Welcome back to CS479, machine learning for 3D data. So before we get started, I'd like to ask about like how is the assignment 1 is going with you. So as you know, the deadline for the assignment 1 is this Sunday. Is there any difficulties with the assignment 1? Is everything going well? So if you have any questions about the assignment 1, please let us know. Please post the questions on the Slack. And after you complete the assignment 1, we're gonna also have the assignment 2 as well. As you know, the assignment 2 and the 3 are already released in our course webpage. And also the thing is that we are using the 2 platforms for the submission. For all the assignments, you will need to use the Grayscope, and you basically need to submit your solution in the Grayscope. And also for the projects, we are also using the OpenReview. So for everything related to the course project, you will need to submit the output to the OpenReview. So that's the thing. And also the thing is that if you have any questions for any of things, like for the lectures and the assignments and also the course project, please feel free to visit our office at the office hour. So we're gonna have the office hour every Monday at the 7 p.m. at the N1 building. So this will be also the offline, the office hour. So please come join us at 7 p.m. today if you have any questions for the lectures, assignments, and the course project. So that's the thing. And also one more thing is that, so we are also using multiple platforms for many things. So we are using Slack, OpenReview, and also we're gonna also use the KLMS. So please set your name in the Slack and the OpenReview to be exactly the same as the name in English in the KLMS. So you do not need to match the uppercase and the lowercase, but please make sure that your name in both the Slack and the OpenReview to be exactly the same with the English name in the KLS. Otherwise, if you do not match your name, we are going to remove your accounts in these platforms. So if you did not fix your name, please fix your name now. So after this lecture, if the names in your account does not match with the name in the KLMS, your account will be removed. So please do that now. And also, yeah, we seen how you basically form the teams for the project. So everyone now basically registered as the team in the OpenReview. So the next step for the course project is that basically you need to also submit the proposal. And the due date for the project proposal is not this Sunday, but the Sunday in the next week. So the deadline will be basically September 21st. And also what you need to submit. So you just need to submit a write-up that includes your idea for the project, the proposal. And basically there's no template for the proposal. You can basically make any kind of the write-up for all the things. But the thing is that you can basically make a document up to 3 pages. So please do not try to make some kind of the long the text. Actually, the shorter is better. And also you need to submit this proposal not to the Grayscope, but to the OpenReview. Obviously, it's basically submitting per team, not for each of the individual. And your proposal basically includes all the information here, and also basically for all the details for the project, everything. Please check out our the webpage. So we are not going to have the time to discuss all the details about this project proposals for many things for the course project, but we are providing all the information in our the website. So please check out the course webpage and basically read every single sentence there. There are lots of some kind of the important information there. So we won't have time to basically go over into all the details for those things. So please check out the course webpage. So the basic idea is that your proposal basically should include all this information. And also, if you do not include those information in your proposal, you may get some penalty. So basically also check out the grading policy in the course webpage. Basically, what are the information that basically you need to include in your project proposal. So you will basically need to include the project title and also the project track, the submission, the ID. So basically, since you already basically registered in the open review, now you have the ID number in the open review. So please use that as your kind of the team ID, okay? So you are basically having the team ID for each of your team, and also the proposal should include all the teammate names, and also you basically need to provide some information for the baseline the method. So there are two important things. The first one is basically the baseline the method. So basically, you will need to choose a kind of the baseline the method that basically meets the following the criteria. The first thing is that the baseline method should be the most recent work, like solving the problem that you are interested in, while basically giving the best performance with the work. So how we basically tell whether the method is basically providing the best performance or not. So you will basically also need to work on basically checking out all the kind of evaluation, the criteria for the given the problem, and how the given the method is basically achieving the best performance based on that. So basically, you will need to do your own survey to basically tell whether the given the method is basically providing the best performance or not. So basically, you need to pick the method that is basically state of the art. So basically, if you pick a baseline method which is not the state of the art, then basically your proposal will be rejected. So that's also an important thing. So it's your responsibility to find the baseline the method. And also the baseline the method should be published on either the archive or any kind of the conference the venue. So that's also kind of thing. And you will also need to find the baseline the method that provides all the code and the data that are used in the experiments. So those are kind of the criteria for the baseline the method. If you also have any kind of difficulties finding the baseline the method, we are not basically providing lists of the baseline the methods for each of the problem, but basically we are providing like lots of the paper the names that are basically related to each of the topic. So please check out the provided the paper list. But basically, you don't need to basically pick a method in the given list. You can basically check out any kind of the other method, and even the papers that we are providing the paper list may not be the state of the art. So you basically need to figure out which one is the state of the art. So finding the baseline the method for the program is also your responsibility. So you basically need to basically figure out what's the baseline the method for the program. And based on this baseline the method, you will basically be able to just pick one of these two tracks of the project. So you can either consider like suggesting a new problem and solving the new problem, or you can basically consider just improving the performance of the given the baseline the method. So the basic thing is that if you choose the novel the problem solving track, this will be the case that you are proposing a new problem based on the baseline the method. So you can consider either choosing either basically changing the input data or the output data. You can basically solve the unsupervised the problem or given some kind of supervised the problem. Or you can basically do some kind of the variation in terms of like making a new problem. You can also consider like using some very new types of data instead of like using some kind of existing data. But in any case, like when you decide to solve a new problem, also the thing is that you basically need to see whether the problem that you're proposing is really new problem, right? So if we basically find that there is actually a kind of existing work that is solving exactly the same problem, then that will not be basically the case that you are solving a new problem, right? So you basically need to do your own survey in terms of like checking all the literature and checking whether the problem that you're suggesting is really a new problem. So that's also kind of the things that you need to basically take lots of the time for that. And if you're also not sure about like whether you're really solving a new problem or not, you can also contact our TS and also ask the questions on Slack. And or you can basically consider solving exactly the same problem that your baseline the method is solving, but you can consider basically proposing some ideas that can basically improve the performance of the method. So that will be the case that you're choosing the performance improvement the track. So if you also have any questions for all the things, please check out our course webpage for more details. And if you still have any questions, please post the questions on Slack. So this is basically one of the most important part in this course, basically finding the right problem for your course project. And if you have any questions with that, please let us know. You can also come join us at the office hour and ask some questions on that. Any questions for the project proposal? Any questions? No question? Okay. So let's move on. So until last week, we are discussing some ideas about basically how we can do some kind of the conversion from the one 3D data representation to the other. And now we are basically starting to basically discuss some ideas about like developing some kind of the neural net architectures that can process the 3D data as input. And we're going to also discuss some kind of the neural net architectures that can also produce the 3D data as the output as well. So today, what we are going to discuss is basically we continue discussing some kind of the architectures that can process the point cloud data as the input. So we are going to discuss the PointNet and the PointNet D++. And I think you are basically implementing the PointNet in the first assignment, right? So we're basically going into some details about the PointNet today. And before that, as we also discussed last time, basically why we discussed the some point cloud encoders. Well, maybe one of the most important reasons for that is that basically many of the 3D data that we are basically achieving, especially from these 3D scanners, are basically represented as the point cloud. So the point cloud is the kind of the natural representation of the 3D data, especially when you basically scan some kind of the physical objects using some kind of the 3D scanners. So basically, if we have some kind of the point cloud encoders, without doing any conversion, we can directly process all these 3D scan data. So that's kind of one of the advantages, like having the point cloud encoders. And obviously, the other advantage is that while we also discuss some lots of the ideas, then how we can basically convert from the one representation to the other, what we also have observed last time is that point cloud is kind of the best representation in terms of the conversion. So it's very easy to convert from any other representation to the point cloud. But actually converting from the point cloud to the other representation was not that straightforward kind of things, because basically we need to have like all the information, like some kind of the surface normal, and also the point cloud should be very clean and the noise free. So given this kind of situation, actually, if we can have some kind of the neural network that can process the point cloud as the input, that can be very useful in terms of that we can basically handle any kind of this 3D data using given the point cloud encoder. So that's basically what we are also going to do in our the first assignment as well. While we're going to also basically work on some kind of the 3D CAD models for some kind of the classification, the segmentation, the tasks that were originally represented as the meshes. Actually, we converted them into the point cloud in a way that we can easily basically process them using the PointNet or the PointNet different architectures. And we can also consider basically, processing some kind of the scan data or some other types of the 3D data using the point cloud encoders. And then the challenges might be is that basically, given that the point cloud does not provide any kind of some regular structures in the data, how are we going to basically process the data using the neural network was basically one of the challenging problem in terms like designing some kind of the neural net architectures that can process the point cloud data. So that's basically what we are going to discuss with the PointNet today. So as we also discussed last time, the problem that we are going to solve using the PointNet is basically this case. So we are taking a point cloud as kind of the input. So we can consider that the point cloud is kind of the 2D array that we are having the n number of the points. And for each of the point, we're gonna basically have like 3 numbers, like x, y, z coordinates. But it does not need to be just like 3 numbers. It can be some kind of basically include some more information. For example, each of the point can have some kind of the color information. Or for each of the point can also have some kind of the surface normal information. So basically, this will be the case that we are taking some kind of the a-dimensional, some kind of the vector for each of the point. Let's say the dimension is the k. So for this would be the case that we are taking this like m by k, the 2D array as kind of input. And based on that, we might basically want to solve some kind of the multiple problems. And one of the problems that we might want to solve is kind of the cases that we want to get some kind of the global information. For example, the case that we are basically classifying the entire object. For the cases that when you want to basically classify the entire object, this will be basically the case that we are basically getting some information for the entire shape. So this will be the case that we are getting some kind of global information, right? Or there might be some kind of the cases that we might want to basically get some kind of the per point information, right? So for example, when you want to segment the given point cloud into some kind of the symmetric parts or some other types of the parts, that basically we might want to get some kind of the labels for each of the point. So there might be the case that we want to get some kind of the per point, the local information, right? So we are basically going to introduce a kind of the architecture that can basically handle both of the cases, either getting some kind of the per shape, the per object kind of the information, or getting some kind of the per point information. Then as we basically also discussed last time, these kind of architectures can be used for the multiple applications, not only for the classification, but also for the segmentation. For example, so in case like when you want to get some kind of the per point the color information, or when you want to basically even predict the surface normal information, whatever kind of the cases, we can basically utilize this kind of architecture for many kind of the tasks. Then how can you basically develop a kind of the neural net architectures that can solve both the problems? So here basically what we want to do is that we want to make the architecture that can actually process a set data. So when we typically talk about the set, the meaning of like having the set data is that the order of the data inside the set does not have any kind of the information. So basically what we want to do is that the point cloud is basically a set of the points, right? So while we are basically going to have some kind of this kind of 2D array, basically the output that we are getting should not depend on the order of the points, right? So however we basically index each of the points, let's say we're going to have the n points here. So, and then for each of the points, we're going to have the index like 0, 1, 2, 3 or something. No, even but when you basically change the order of the points, when you basically index the points in a different way, what we want to do is that we want to get some kind of the output. So we basically want to guarantee that however we basically order the given set of the points, we basically want to make the architecture that can guarantees to basically provide the output. So that's basically the property that we want to achieve. So we can say that this is basically the property that we want to achieve as kind of the permutation, the invariance, and the equivariance. So which means that however we basically permute the order of the points, we always want to get the output. So that's the case of the permutation, the invariance, right? And what's the meaning of the permutation equivariance? The permutation equivariance basically means that if we change the order of the points, then the order of the output is also changed. So the permutation invariance is for the case that when you want to get some kind of the global information, right? For example, when you want to get some kind of the label, basically the classes of the entire object, then the label of the entire object should not be changed based on the order of the points, right? So that's the cases for the permutation, the invariance. But for the cases of like getting some kind of the per point information, if we want to get some kind of the per point, some kind of the part labels or something, then basically if we change the order of the points, then the order of the output also should be changed based on the changes of the order of the inputs, right? So that's the cases that we want to achieve the permutation equivariance. Basically, the order of the input and the outputs are basically changed in the same way. And we are basically making a neural network that can basically guarantee this kind of the properties. So that's basically the one property that we want to achieve using some kind of architecture that can process the point cloud data. And also, what will be the other property we want to achieve? So basically, given some kind of the some 3D data that are basically describing some kind of the 3D objects or some 3D scenes. However, basically we transform the given kind of the point cloud with some kind of the rotation and the translation, we basically might want to basically get the same results, right? So basically here in this example, like however we rotate this airplane shape like this, basically rotated the airplane should be also the airplane, right? Which means that however we basically rotate or translate the given 3D shape, the output of the class labels of the entire shape should be exactly the same, right? So that's basically also the property that we want to achieve. And also this property can be called the transformation invariance. So basically, however basically we rotate or transform the given kind of the point cloud, the output should not be changed. And so the question is that how we can basically make a neural network that can guarantee this kind of the property. So these two are the most important kind of things in terms like designing some kind of architecture that can process the point cloud data. Is this clear? Any question on this? So if we say the same thing, like slightly more the formal way. So basically what we want to do is that especially for the permutation, the invariance, in terms like when you basically define some kind of function. So basically here, this function is the neural network, right? So when you basically make a neural network that can basically take a set of the data as the input, we want to make the function that basically guarantees this like the permutation, the invariance, which means that when you basically just like change the order of the points like this, the output should not be changed. So that's the property that we call the permutation invariance, right? So it's the only matter of like how we define this kind of function that guarantees the permutation, the invariance. And also the other property would be is the permutation equivariance. So this will be also the case that when you also make a function that basically give us some kind of the per point the output like this. If we also change the order of the points, the input the points, the data, we want to basically guarantee that the output, the order of the output is also changed in the same way. So we also want to make the function, a neural network that can basically guarantee this kind of the permutation, the equivariance. So which basically means that the architecture that we want to basically introduce here is a kind of architecture that can process any kind of the set data, right? So when you basically have any kind of the set data where basically the order information does not matter, basically the order does not have any kind of the meaning in the given the data. We will basically want to utilize this kind of the functions that basically guarantees us the permutation invariance or the permutation the equivariance. So this is basically the cases that we want to basically develop. So basically, and also the cases like having this kind of the permutation, the equivariance, this kind of the function that guarantees the permutation, the equivariance is also called the symmetric function, right? Which basically means that if we change the order of the input, then also the order of the outputs are basically changed. So basically, this is the kind of the cases that we want to make. Then the question might be is that what will be such kind of the symmetric functions? So however we change the input data, if we also see the same change of the order of the outputs here, what will be such kind of the function that we want to get? So let's first think about some kind of the cases that we want to get some kind of the permutation invariance, right? Which means that however change the any kind of for the any random order of the input, we guarantee to get the same the outputs, right? So there can be multiple such kind of the cases, as you already posted on the Zoom chat. Basically taking a sum or the product will be all the cases that we also basically guarantees the permutation invariance, right? Was taking some kind of pooling, like the mean pooling or the max pooling, also be the case that we are making some kind of symmetric functions, right? Taking the average, also the same case that we are basically achieving some kind of symmetric function, right? Then based on this kind of like some, possible the candidates for this symmetric function, then the question might be is that how we are going to basically design some kind of the architecture that can process the set data. So one simple kind of the observation here is that if we basically make this kind of the combination of the functions like this, so we are basically having a function that can basically process each of the data point, individually data point, independently like this, with some kind of shared function h here, right? And then we are going to basically aggregate all this kind of the per data point function into using some kind of a symmetric function g, right? So that basically plays the role of basically aggregating all the information for each of the points. And then we can consider basically further processing the output of this symmetric function, right? So basically, if we design a neural network in this way, basically having this kind of function as kind of the one of the layer in the neural network that basically have some kind of the shared function that process each individual data point and aggregating all the per point information using some kind of symmetric function. And also further processing the output of the symmetric function using some kind of the other function. So if we have like this type of the combination of the function as kind of the one layer in the neural network, then the output of like this combination, the result of like this combination, the function will be also another symmetric function, right? So that will be basically the basic idea in terms of that we are basically developing some kind of some neural net architectures that is basically becomes basically symmetric function. So that's the basic idea of the PointNet. So what be kind of the candidates that we can use for each of the H function, G function, the gamma function here? So if we think about any kind of, using some kind of, for example, like PyTorch, kind of some library that can help us basically build some kind of neural net architectures, what would be kind of the functions that we can use for each of the H, G, and the gamma, right? So any answer for this? Yeah, these will be basically things that you should be implementing your first assignment, right? Yeah, so we basically want to use any kind of the linear layer for both of the H and the gamma function, right? So it can be any kind of the linear layer, basically NLP, for each of the H and the gamma. And for the G, for this part, only this G need to be basically symmetric function. So we can either use the summation or the product, or we can use some kind of the max function or the mean function, any kind of symmetric function. So that will be the basic idea for the PointNet. So this is quite easy. So basically, also the thing is that then how we can also achieve some kind of the transformation in the invariance. So this is slightly more the complicated kind of things. So given any kind of the 3D data, but basically we want to make a neural network that basically guarantees this. Like, so even when we apply any kind of transformation to the given data, we might want to see that the output of this function with the transform the data to be exactly the same with the output of the original the 3D data like this. So the question is like how we can make the neural network that can process this kind of the invariance to the transformation. And also it might depend on the transformation that we are interested in. What will be kind of the transformation that we might want to interest in. It might also depends on the applications. But for example, like for the classification, for example, like if we want to classify the given the 3D shape, the 3D objects represented as some kind of the point cloud, we might basically want to achieve the rotation invariance, right? So however, basically we rotate the 3D shape, we might basically want to give some kind of same label, same the class D label for the objects. And also we might want to give some kind of the translation, achieve some kind of translation invariance as well. So however we basically translate the 3D object in the space, the output should be the same. But how about the other types of the transformations? For example, like scaling, right? For the uniform scaling, basically we might also want to achieve the invariance to the scales, like how we basically enlarge or shrink the size of the object. The class label should be the same. But depending on some kind of the cases, we may not want to get some the invariance to the anisotropic scaling. For example, the cases like when you have a kind of the chair like this, if we basically enlarge this chair along this direction, like having this kind of a chair, then we might want to call this not a chair, but a bench, for example, right? So this might be kind of the case that we don't want to achieve this scale invariance. So it all depends on the kind of the application that what we are basically solving. Or there might be also some cases that we might basically we may not want to achieve some kind of the reflection invariance, depending on some kind of applications. So those are basically all the kind of the application depend on some kind of the situations. So depending on which problem that we solve, actually we might want to achieve the transformation, the invariance, where we may not want to basically achieve the transformation, the invariance. So it all depends on the situation that we are solving, right? But let's think about the case that we want to achieve some kind of the rotation, the invariance. How we can basically make a neural network that can guarantee us satisfying the criteria, achieving the rotation, the invariance. Actually, one thing is that there are also kind of lots of the research going on, like developing such kind of architectures. And this is actually really non-trivial the problem. There are kind of lots of kind of things that we need to consider in terms like guaranteeing the rotation, the invariance, or some like other kind of things. But basically, what we are going to see here is that we are going to see a kind of the architecture that does not guarantee the rotation invariance, but that can help us when we basically have some kind of the 3D data with the random rotations. So the thing is that this architecture does not guarantee us to basically achieve the rotation, the invariance, but basically this can basically help us when we basically have some kind of the 3D data with the random rotation. So the basic idea of like this spatial transformer network, which was introduced in about like 8 years ago, 2015, is that basically, and also this network is not related to the transformer, the network that we know. This is not about that transformer. So this is another the transformer, which is the spatial transformer networks, introduced like 8 years ago. And the basic idea of like this architecture is pretty simple. So what they do is that we are making some kind of the small neural network that is basically plug into the given the architecture in a way that the basically small network basically plays the role of basically aligning all the given kind of the data point, all the 3D data basically in our case. So basically this idea was not first used in the PointNet, but actually this idea was actually first used in the some 2D convolutional neural network. So the basic idea is that we are having some kind of the small architecture, small neural network in the whole neural net pipeline in a way that this small network actually plays the role of basically aligning all the kind of the given the input data into some kind of the canonical frame. So this is kind of the example that we are having some of the images of the traffic signs. So when you have some kind of the images of the traffic sign, there can be some kind of the all the random cases that we are having some kind of the having some images with the different transformations. So this might be the case that we are basically scaling up or scaling down of the given kind of the traffic sign the images, or this might be the cases that we are having the images with some kind of the arbitrary rotation. But actually, in the neural net perspective, as we have some of the images with all the random transformation, this is the case that we are having the diversity of the images that the neural net needs to memorize, right? Does it make sense? So as we have some kind of the more kind of the images with all the diversity transformations, for the neural net perspective, like training all the things, like all the images with some kind of the arbitrary transformation, it's actually like all the different data. So these are all the kind of the patterns that the neural net needs to basically memorize to basically conduct some kind of the tasks, like some kind of the classification or segmentation of the things. And the thing is that basically, as we basically reduce the diversity of the data set, actually the network will be much easier to be trained, right? So what we do is that we are having another like the similar neural network that basically help the rest of the part of the neural net in a way to basically reduce the diversity of the input data in terms of basically aligning all the data into some kind of the canonical frame, like having some kind of the the size of the images and also kind of the orientations of the images in a way that we can basically reduce the diversity of the input data so that the training of the rest of the part of the neural net becomes like much easier. So that's kind of some kind of the hacky way that we can basically handle some kind of data with some kind of the random transformations. even if the image was upside down, STM would be able to rotate it to the correct way. So basically, there is no guarantee. So the thing is that we are basically having a kind of like some kind of the small D neural network that might basically help us in terms of basically reducing the diversity of the input data. So basically, there is no guarantee that basically this small D network will really basically align all the data into the canonical frame or not. So that's kind of some hacky idea, right? So basically here, there's no theoretical guarantee whether this will be basically help us to basically do some kind of alignment or not. So but it might be actually interesting for you to try this yourself. So actually one more thing is that in the first assignment, you can basically consider basically implementing this spatial transformer into the PointNet. Actually, but the thing is that the data, we're also going to discuss the data part as well, but the data that we are providing is actually already having the 3D models that are all aligned in terms of the rotations, which means that if all the data are basically already aligned in terms of the rotations, you do not need to have this spatial transformer. All the 3D models are already basically aligned. So which means that without having this spatial transformer, you will be actually able to achieve some kind of the good performance in the case when the 3D models are all perfectly aligned. And actually, that's the case that we are providing as kind of the model, the data as kind of for the experiments. So you'll see. So basically, in the first assignment, you don't need to implement this part. Actually, we already provided all the code for this spatial transformer. So even you don't need to implement this, but even you don't need to plug in this into the pipeline because the 3D models that we are providing the data set are already aligned. So that's kind of things. But what we strongly recommend you to check out is that when you randomly arbitrarily rotate all the 3D data for the input, basically, if you do not have this spatial transformer, then you will see that the performance of the PointNet is decreased a lot. Okay, but when you basically also arbitrarily rotate all the 3D models, if you plug in this spatial transformer, then you will see that for some of the cases, this small architecture is basically automatically aligning all the input data into some kind of the canonical frame in a way that the rest of the part basically can improve the performance. So I strongly recommend you to check out yourself for this using the code that we are providing. So what you can do is that you can basically apply some kind of random transformation, random rotation to the input data and see the difference between the case that we are having this spatial transformer and you are not having this spatial transformer, and what's the kind of the canonical frame that the neural net might learn, right? So actually, the canonical frame that the neural net learns may not be this kind of the right kind of the abstraction. So this might be the case that the neural net actually might learn some kind of the canonical frame. Basically, having some kind of a slanted angle for some of these 3D objects or something. So check this out yourself. And also one more question, that to deal with the point cloud translations, would learning a 4x4 transformation matrix would work better? Well, yeah, you can also consider like not just having the 3x3 matrix, but also the 4x4 matrix for the applying any kind of the affine transformation, right? That this might be a case that the neural net can also basically do not only rotation and the translation, but the neural net might also do some kind of scaling or sharing all the other things that are basically included in the affine transformation. And also the thing is that as we basically provide more the flexibility in terms of the transformation, so not getting the 3x3 rotation, but as we basically provide more the flexibility in terms of learning some kind of the bigger the type of kind of transformation like affine transformation, actually it might help or it may not help because like if the neural net has some more flexibility, it might basically have some more difficulty to learn the canonical frame. So I also recommend you to check this out yourself. What would be kind of the right basically scope of the transformation to learn to deal with some kind of all the data that you're having. So this basically means that given any kind of the 3D data you have, obviously the best way is that if you can do some kind of the pre-processing in terms like aligning all the 3D data, that will be the ideal case. Then you don't need to worry about any kind of the transformation, the invariance. You don't need to even use this kind of a spatial transformer and see that the PointNet like the architecture actually works quite well. But in the case that when you cannot basically do any kind of pre-processing, like in terms of aligning the 3D data, then you can consider like plugging this kind of some kind of architecture. This still does not guarantee any kind of the transformation, the invariance, but this might help to basically achieve some kind of like in terms of reducing the diversity of the data and basically improving the accuracy for the rest of the pipeline. But also this does not guarantee to improve the performance for all the cases, but this may help. So that's also kind of the some kind of risky part in terms of utilizing all the things. So the question here is that make transformation metrics depend on the input tree data. How do you make it model search transformation function automatically? Well, I mean, the TNet, yeah, so what we are going to see is that we are having some kind of the small D architecture here. In a way that like for this kind of the case, especially in our case that we want to basically make some kind of the apply some kind of the rotation. We are making a small network that is taking the given point cloud as the input and then basically producing a 3x3 matrix as the output. So for this small network, which is called the TNet, this is taking the point cloud or some kind of the, yeah, basically the point cloud as kind of the input, and then basically outputting a 3x3 matrix as the output. Then obviously here the question is that, no, we don't know whether this output 3x3 matrix will be really a rotation matrix or not, right? And here one quick question is that what are the conditions for a 3x3 matrix to be a rotation matrix? This is a question. Is everyone following the question? So the question is that what are the conditions for a 3x3 matrix to be a rotation matrix? But yeah, this is quite basic things for the, like all the some graphic vision things. Basically, for the rotation matrix, there are two conditions. Like the one condition is that the matrix should be, you know, orthogonal the matrix. And the other condition is that also the determinant of the matrix should be 1, right? So also there are lots of kind of the interesting the idea in terms like, you know, how we are going to make a neural network that can predict some kind of the some rotation in the 2D, especially in the 3D space. And then we can use some kind of like different representations for the rotation. If you took the computer graphics course, then we can also consider using some kind of the quaternion. Is there anyone who knows like quaternion? Does everyone know quaternion? Yes or no? Yeah. So yeah, you can consider like predicting the quaternion to represent some kind of the 3D space the rotation, or you can also predict like axis angle of the some in the 3D space. Actually, there are a bunch of the way that we can also basically represent the rotation in the 3D space. So you don't need to actually predict 3x3 matrix. You can actually predict directly like axis angle of this 3D rotation, or you can also predict some quaternion. But one way that we can also do in terms of like predicting this 3D rotation here is basically predicting a 3x3 matrix, and then enforcing this 3x3 matrix to be one of the rotation D matrix. So the idea for that in this paper is basically adding this regularization in a way to basically making the rotation D matrix to be a orthonormal D matrix like this. What do we kind of the problem like having this regularization? This is really important question. The difference of the kind of the quaternion axis and change the performance. Yes, this is really important question. Actually, depending on the representation that we are using for the 3D rotation, actually the performance varies a lot. The performance varies a lot. So this is like all the kind of the interesting the kind of things for the neural net training. So like, depending on like how we represent all the data, actually the architecture even can be changed. And also in any case, like the depending on the representation, the performance of the neural network can be changed a lot. So actually there are lots of kind of discussion in terms of like what we kind of the best representation in terms of representing the 3D rotation. So before I introduce before I describe the answer that question, let me basically finish this first. So when we have like this regularization in terms of like getting the 3D rotation, what are the kind of the problems with this? Actually, one thing is that I told you that there are two conditions for a 3 by 3 matrix to be a rotation D matrix, right? This regularization only guarantees us to basically have the orthonormality, but this does not guarantee us to have some kind of the to make the determinant of the matrix be 1, right? So what happens if the determinant of the matrix is not 1? So let's think about the case that when you have the orthonormal D matrix, if the determinant of the matrix is not 1, then what do we get? Yeah, so if we basically have a 3 by 3 matrix, which is like orthonormal D matrix, but if the determinant is not 1, then the determinant will be -1. And that's the case that we are basically doing some kind of reflection in matrix. So we can also consider adding some kind of the extra regularization here. But basically, yeah, this is kind of the simple case that we are either getting some kind of the rotation or the reflection in a way to basically align all the 3D the given data. But this will be also the case that we are just like adding a extra the loss function in the training, which does not mean that we are enforcing the neural net to make this the output the matrix to be a orthonormal D matrix. But also this does not guarantee that the output to be a some real the 3 by 3 the 3D rotation D matrix, right? So we are not gonna get into some more details here, but I'm gonna post the some kind of the resources later. But actually, there's kind of the way that we can basically project any arbitrary 3 by 3D matrix into the closest 3D rotation D matrix in a kind of differentiable way using the SVD, if you took the linear algebra course. So instead of like having this kind of the regularization the loss function, we can actually just find the closest the 3D rotation D matrix from the given arbitrary 3 by 3D matrix. So precisely this is the case that we are doing some kind of projection from the 3 by 3 matrix to the closest 3D rotation D matrix. And then we can actually utilize this kind of the projected the 3D rotation in this case. And this is kind of like one way that we can basically predict some kind of 3D rotation. And this is known as kind of the best way to predict the 3D rotation compared to the other cases of like predicting the quaternions or the axis angle, some other things. Yeah. So actually we can discuss more on that. But yeah, these are some kind of tricks in terms of like, predicting some 3D rotations. And so yeah, basically the answer for the question, like depending on the representation of the 3D rotation, whether the performance of the neural network varies a lot or not, the answer is yes. Actually, it's really important to choose the right rotation for the everything, and also for the 3D rotation as well. So this was kind of like simple idea in terms of like achieving some kind of, not achieving, but somehow like handling some kind of 3D data with the arbitrary rotations. And as I said in the first assignment, I also strongly recommend you to check out what happens if you start to arbitrarily basically rotate the input 3D data, then whether still the PointNet without the special transformer still works or not. So you can check that out yourself. And when you also plug in this specialty transformer, whether it can really help to improve the accuracy or not, you can also check that out yourself. So that will be also interesting to see. How does just adding L to the spectral get back to the TNet matrix output only, since we have other nodes in the computation graph? Well, we can just like add the loss function only for the parameters of this input and the parameters of this network. Then this will basically directly apply back to this part of the neural net. So it's basically like making some kind of the computational graph from this regularization the loss directly back to the kind of the parameters of this TNet. If the determinant is not 1, then there's no volume preservation. -1 will be reflection. Yeah, as I said, yeah, adding this regularization does not guarantee to achieve some kind of like only the rotations. It actually might basically result in some reflection as well. but it only affects the TNet. Well, I mean, it affects not only to the parameters of the TNet, but also to the input to this TNet. So this is the case, and now the input to the TNet is just like the point cloud here. But we're also going to see that actually this TNet can be applied not only to the first layer, but also can be applied to some other kind of the layers in the neural network. Then there will be the cases that it is basically backpropagating through the TNet and to all the kind of the input to this TNet, basically into some early stage of the neural network before this TNet. So let's get into the neural net pipelines, a little bit more the details. So let's think about the case that we are basically having the m/3, the 2D array. But obviously this will be the case that we can have either not only the x, y, z coordinates, but it can be a case that we are having some more the kind of the values, like not only x, y, z, but some kind of extra kind of things. So it might be case that we are having the m/k the matrix. So anyway, we're gonna basically have a kind of the the TNet, basically the spatial transformer in terms like basically putting some kind of the 3D rotation or the reflection in a way to basically align all the input data. And after that, we're gonna basically have the shared MLP, which is like applied to all the individual point. So this will be basically the case that we're applying this kind of like linear layer, the same linear layer into all the individual points, because we don't have any kind of the index information for each of the points. So we're gonna basically apply the linear layer for all the points. So implementation device, what we can do in terms of making the shared MLP is that instead of like having some kind of the function call for the linear layer, you can just simply use the 1D convolution the layer. So 1D convolution will be the case that it's exactly the same, which basically just like processing each of the one-dimensional vector as the input and making some kind of linear layer. But it will be much easier in terms of like sharing this kind of the layer into the multiple points. So it's kind of the implementation, the tip. So if you use the 1D convolution layer, this will be the case that still we are making some kind of the linear layer for each of the point, but we are sharing the 1D convolution corner for all the points. So that's basically what we want to do, right? So having like one single MLP, but which is shared into all the input points, right? So we can basically map all these kinds of like three-dimensional input vector into some kind of the arbitrary dimensional vector for each of the point. So let's say the dimension is now the 64, right? And the thing is that in this kind of a high dimensional space, where basically all the points are mapped into some 64 dimensional space, we can also do the same thing in terms of like some kind of the alignment. So I mean, this is kind of the optional things, but we can consider basically applying the same TNet into this like high dimensional space as well. So this is optional. I mean, this is not necessary, in terms of like getting some kind of the good performance. But just we are saying that this is kind of like doable in terms of like applying the same TNet not only in the 3D space, but also in this 64 space as well, in terms of like doing some kind of the additional alignment as well. And then we can basically also do some kind of transformation, and we can repeat the same thing. So basically here, this means that we are repeating this kind of the layer 3 times in terms like increasing the dimension of each of the vector to the 64, to the 128, to the 1024. So basically making some multiple layers in terms like increasing the dimension for each of the point to be 64. So basically also this 264 basically means that we are also repeating this process twice. Basically increasing from the dimension from 3 to the 64, and then 64, and then 64 again, and then 128 and 1024. Actually, the dimension, the number of dimension here is not that important. You can also try to vary these numbers and see how much these kind of numbers affect the final outputs. Wouldn't be the 1D convolution to be identical to using a 1/3 convolution in this case? Yes. Obviously, using the 1D convolution is exactly the same case like applying some kind of 1/3 convolution. Yeah. Is this clear? So this is basically nothing but basically just, we are just keep using some kind of the 1D convolution in the multiple layers in terms of like applying the same linear layer for each of the point, and just applying some kind of some transformation, the special transformer architectures for some kind of the output, the point clouds. Then what we get is that we are basically, increasing the dimension of each of the point features into 1024 like this. And as we discussed in the previous slide, this will be basically, these are all the cases that we are basically processing all the individual point using the same function. So we are basically treating all the points independently using the same diff function, but there is no any kind of some global the operation. And once we basically have this kind of like per point of the operation, now we want to basically make a kind of symmetric function in terms of like adding some the pooling operation. So now we use the max pool here in terms of like making a symmetric function, right? In a way that now we get the global feature. So basically this feature will basically includes all the information for the entire shape, and then we can further process this data using the linear layers in terms of getting some like some output the values for the entire shape. I was mainly used on how many learned concepts we have as on as a depth-wise computation. Three different numbers. Well, I mean, this will be basically the case that we are having the linear layer for the XYZ. So this will be basically the case of like learning some kind of the matrix that we are having the XYZ and basically returning the 64 dimensional vectors, making this kind of the 64 by 3D matrix for each of the XYZ the channel. So obviously this will be the case that we are having some kind of transformation for each of the XYZ channel. Right? Any question on this? All rules are the same. What do you mean by all the rules are the same? All rules. Why? I don't know why the all rules are the same.
Because it's shared, the parameters are shared, right? So
no, I mean these entire matrix are shared into the all the points. But this is not the case that we are having the same rules for this matrix. The entire matrix is basically shared for the across the all the points.
Okay, so when we mean shared, what do we mean then? Because from my understanding, I thought that every point is transformed in the same way. So yeah, all those 64 rows would be the same in my mind, but apparently it's not. So what do we mean by shared?
Well, I mean, like we are basically multiplying this 64 by 3 matrix, the same matrix into the all the points. But it's not this case that we are basically having the same rows in this matrix. We are sharing the entire this linear operation into the all the input points.
So each input point can be transformed in a different way.
No, it's basically transformed into the same 64 dimensional vector.
Okay.
So the linear operation is shared, and the linear operation is basically mapping the 3-dimensional vector into the 64-dimensional vector.
Okay.
Any other questions? Well, yeah, so this is basically the case that we discussed in the previous slide in terms of that we are having the per point some kind of operation which is shared across all the points. Was the channel X column size? Okay. X column size. Yeah, channel X is the corner size. Well, I mean, yeah, this will be, as I said, like this will be a case that we are having some kind of linear layer mapping each of the 3-dimensional vector into the 64-dimensional vector. Make sense? I mean, simple NLP. No more questions. So yeah, so basically we are having some kind of the long pipeline for each of these H, having some multiple layers with some kind of the specialty transformers. And then we are having the max pooling operation here in terms of making a symmetric function and we are having some linear layers in terms of like processing the global features, we know way to basically define a kind of architecture that basically guarantees the permutation, the invariance. So that's the basic idea of the PointNet. Right? Any question on this? And then what we are going to do is that we want to basically also extend this idea, not only to get some kind of the global information, but also to get some kind of the per point information as well, right? So what we can do is that basically, as we have seen in the previous slide, until this step, we are getting some kind of the per point information, right? Each of this kind of the row here is basically representing some kind of the high dimensional the feature vector for each of the point. Then we can directly actually consider using this kind of the per point feature here in terms of getting some kind of the per point information, right? Then what would be a problem if we basically directly use this kind of the per point feature in this step? Another question. So here the question is that no, until this step, right? This basically corresponds to the h function here. But what we are basically going to do is that if we directly use this per point feature to get any kind of the per point the output in some kind of the tasks like some segmentation, if we do directly use the information for the per point the prediction, what would be the problem with that? Well, I mean, this will be the case that we want to achieve the permutation equivariance, right? So when we also change the order of the input, the points, the order of the points, we want to also change the order of the outputs. But actually, like this basically obviously like guarantees the permutation equivariance, right? Because we are just like treating all the points independently using some kind of the shared the network. So in terms of achieving the permutation equivariance, there's no problem with this. Yeah, obviously the problem is that there's no global information. So like for any kind of the point, let's say this point has like some kind of the x, y, z coordinates. Whatever points we have in this kind of input point cloud, if we directly use this point feature, this feature is only basically seeing this x, y, z coordinates, only the coordinates of like this single point, not seeing any other the points. Which means that like whatever kind of the point cloud that we have, for the given the point with some kind of specific the x, y, z coordinates, the output of this point will be exactly the same, right? So this is not the case that we want to see. We want to basically determine the labels for each of the point, not only seeing that specific point, but also seeing the entire shape. So this will be the case that we are not having any kind of the global information, but the feature only actually includes the information of the like single point, the corresponding the point. So obviously that is really kind of the case that we are only seeing that single point to determine the label of the point. So that's not the ideal case. So basically we want to basically combine some kind of the local feature, given here or here, with some kind of the global information. And the simplest way to basically combine the local and the global information is to basically just like combine them, the concatenate these two features. So we are taking the per point feature here with some kind of the global features here. So what we do is that here we are basically having all the per point features, and we are basically concatenating the global features while repeating that into each of the point. Then what we're gonna see is that each of the row here will basically have the information for each of that point, the single point, and all the global the objects. And then we are also using the same architecture in terms of having the shared the MLP for each of the point in terms of getting some kind of the final the outputs for each of the point. Does it make sense? Any question on this? Good. Yes. Yeah. Very simple the architecture. So this is the simplest architecture we will see over this the course. So based on that, what we can do is that we can do some kind of the task like the classification and the segmentation. So like some kind of the very simple the data set that have been used about like like more than 8 years. It's basically like the ModelNet data set that only actually just have like more than 10,000 the CAD models. So as I said, like we can basically convert all the CAD models into some kind of the point clouds and test our the point cloud, right? And these will be also the cases that we are having the full T classes, the objects. And we can basically, so, and this is the data set that you are basically using in the assignment 1, right? So you can test basically how much the accuracy of the classification that we can get. And the interesting thing is that actually this is the table actually we have seen in the second lecture 2 weeks ago. Do you remember this table? So actually we have seen this table last time. And actually, when you compare the PointNet with the other architecture that takes the other representation as input for the cases that we are taking the block cells as the input, and also the multi-view images as the input. So these are the cases that we are taking some multi-view images as the input. And these are the cases that we are taking some voxel representation as the input. You can see that actually the performance are basically almost kind of the comparable for those kind of the cases. And actually we can get the best results when you use the AT images in the multi-view image cases. But compared to those kind of the cases, the advantage of the PointNet is that basically this is the case that we are basically utilizing some kind of 3D convolution with a very low resolution, 30 by 30 by 30. But even with this kind of like very low the resolution, like 30 by 30 by 30, the numbers that we are basically using, the number of the values that we are using to represent a single shape would be basically about like 27,000, right? But compared to that, basically, this will be the case that we are only using the 1,024 points, which means that each of the shape will be represented with just like more than 3,000 the number of the values, which is like way smaller like size of the data representing the same the 3D shape, right? Which means that even by just like using the 3,000 the number of the values to represent a single the data point, we can actually even achieve some kind of better accuracy in the classification. How about the case like comparing with the multi-view images? Actually, this is the case that we are using lots of kind of the very huge scale kind of the data to represent a single the 3D object. And this was actually the case that we are having the AT images. And each of the image has the resolution of the 164 by the 164. And for every single the pixel, we're going to have the RGB the values, right? Which means that now a single 3D object is basically represented with like this number of the values, more than 6 million number of the values, which is way bigger than the number of the values that we are using for the PointNet. So compared to the cases that we are having the point cloud representation, which also has the very low resolution, just like with some like 1,000 points, the cases that we are using the multiple images might be the case that we are having about like more than 2,000 times bigger the scale of the data to just like represent a single point, while basically achieving some very marginal improvement in the accuracy, which means that the PointNet is like way more effective the architecture that can do the same job. Does it make sense? And here also the question is that why do you use the 64-dimensional vector instead of like 1,024-dimensional vectors? Well, actually, yeah, you can use the, sorry, yeah, let's go back to here. Yeah, instead of like using the features here, actually you can use the features here. Yeah, you will see that, I mean, there's no big difference. Okay, the only reason that we are using the features here is that even just by using the features here, we can actually get some kind of the good accuracy for most of the cases. That's the only reason. But you can actually use the features, feature vectors as the output of like this layer, 1,024-dimensional vectors. And this might basically provide some more information for each of the point. But it's in practice for most of the tasks like the segmentation and the classification that we do, actually just using this 64-dimensional vector is giving us already kind of the good accuracy. So that's the only reason. But actually you'll see that, so I also recommend you to basically make some kind of the variation of like this architecture and see how much the variation basically affects the final outputs. And that's this, trying this kind of some kind of the variations of the architecture will be also the things that you will need to do for your the course project as well. So try yourself and see how much it affects the final the outputs. Any questions on this? Yeah. So and also we can apply this kind of the architecture for the segmentation as well. One question about the transformation. Offline transformation, working using non-linear transformation. Well, so it all depends on like what sort of the transformation basically you want to consider in terms of achieving the invariance. So as I said, this was the PointNet was the case of like only considering the 3D rotation, but we can also consider achieving some kind of the translation invariance or scaling invariance or some other types of the invariance. But that might also depends on the application. For some of the applications, like applying some specific types of the transformation is actually really changing the data. For example, as I said, like, for example, when you have this kind of the chair, if we do some kind of scaling along this axis, this will be the case that we are making the chair to be a bench. Then we might want to give some kind of different label for the data. So for those kind of cases, we may not want to achieve some kind of the some scale invariance, right? So depending on the application, we might consider some other types of the transformation, the invariance as well. Obviously, also guaranteeing the transformation, the invariance is really challenging problem. So this was kind of reason like we handle all the things. So coming back to the segmentation, the case, actually ShapeNet is another data set that people are using both for the classification and the segmentation, the tasks. This is also quite old data set. Obviously, there are also kind of new data sets as well. But in this kind of some toy data set, now we are having a much smaller number of the classes, only 16 classes, which means that you can also try the classification network with the ShapeNet data set as well. And also, this is the case that each of the class has the some kind of the part labels from the 2 to the 5 the part labels. So in total, I know that there are about like 50 the part labels for each of the point. And basically, you will need to implement the segmentation architecture of this ShapeNet in a way to basically assigning like one of these kind of like 50 labels, the part labels, for each of the point in the shape. So you're gonna also need to implement that. And we can also do this kind of segmentation not only for the parts in the objects, but also for the objects in the scene. So there are also lots of kind of the data set doing some kind of the object segmentation, some semantic segmentation in the 3D scenes. And this is also one of the old and well-known data set, basically segmenting the objects in some kind of indoor scenes, which is known as called the Stanford 2D, 3D the scene data. And for those kind of the old data set, also the PointNet provides some kind of the best performance in terms of like beating also all the previous the 3D convolution neural network. So before we wrap up all the things, actually the most important thing in the PointNet is that actually this PointNet is quite robust to some kind of the corruption or some missing data into the input the point cloud. So actually this is quite important part in the PointNet. So this basically graph shows that given some kind of the point cloud, even when it basically miss the 50% of the data, the only kind of the accuracy drop that we are getting with this kind of like missing the 50% data is only 2%, which is quite good, no? So even when you have some kind of the neural network trained with the 1024 the points, and when you only provide 512 the points as the input, we are still getting the quite good accuracy in the classification the task in terms of like only losing the 2% of the accuracy in the classification. Right? The question is that those two tasks are different part of the scene segmentation. Well, I mean, these two are the same in terms of the neural net implementation. Whether you basically do some kind of the part segmentation in the objects or the object segmentation in the scenes, both of these two tasks, the cases will be the case that we are predicting some per point labels. So in terms of like neural net, the architecture, the design, and the training, these two are exactly the same case. You can use the same architecture just with a different data set. Make sense? So yeah, let me just finish with this one. So this will be basically very important the fact that even when you basically lose lots of the data in the input, Basically, the neural net, the PointNet is quite robust in terms of getting some kind of the very high accuracy with some very small the decrease in the accuracy of the classification of the test, which is very different with the case that we are using some 3D convolution neural net. So compared to the case that we are using some 3D convolution neural net, when you basically use the PointNet, the network basically performs quite well even when you do lots of the data. And do you see why we are achieving this kind of the robustness to the data corruption? Any guess for that? Any thoughts like why the PointNet will be way more robust to this kind of some loss of the data? Next pool. So yeah, I mean, it's really need to think about this point, like why the PointNet will be more robust to the other kind of the architectures using some like other representation like 3D the voxels or some kind of multiple images. And the thing is that some kind of secret here is that we are using the max pool as some kind of symmetric function. So we could use some kind of the summation or the product, other types of the symmetric function here at this point as one of the symmetric function. But instead of like using some summation or the product, we are using the max pool as kind of our symmetric function. So this is basically the case that like when we have this kind of like 1024 dimensional vectors for each of the points, so we are having the n points, and for each of the point, we are having this like 1024 dimensional vectors. And what we do is that we are taking only the max value for each of the dimension, right? Makes sense. For each of the dimension of these 1024 dimensional vectors, we are taking only the max values for each of the points. Then this means that there will be some points that are basically contributing to give the final alpha here. So if the point basically includes the value, which becomes the maximum along this dimension for each of the dimension, then this point is contributing to the final alpha, right? But there might be some of the points that are not contributing the final alphas. So there might be some points which value for each of the dimension is not maximum for all the dimensions in the feature vectors, right? So we can basically define some critical points. So here, what critical points basically means that these are basically a subset of the points that are contributing to the final output of the max pooling, which means that these are basically a set of the subset of the points that basically includes any of the value that becomes the maximum for that dimension. Make sense? So we can consider like, for example, like if we have like 1024 points and having 1024 dimension, then in some very specific case, maybe all the points can contribute to final the global feature, right? But for most of the cases, basically when one point contributes to the like giving the maximum value in the 2 dimension, which means that there might be some of the point which is not contributing to the final the outputs. So we can consider basically taking this like a subset of the points, which is giving some kind of the final value in the after the max pooling. Then if we visualize this like subset of the points, then we get this. So this is the input the point cloud, and this is basically visualizing the final the critical points. And as you can see, actually some of the points that are on some kind of some kind of edges of the shape, or giving some kind of geometric some descriptions of the points are basically picked as kind of the critical points, which means that like when you basically miss some of the points inside of this kind of shape, which basically becomes not the critical points, the final output is not changed. So given the set of the points, when you basically miss some of the non-critical points, the output is not changed, which means that the neural net basically automatically learns some kind of the important the points that are giving some kind of the geometric features, and which also means that when you miss some of the points that are not the critical points, the output is not changed, which means that the neural net becomes like more robust to basically missing some of this kind of information that are not giving some kind of the critical information for the to decide some kind of the classes to the objects. So that's the very interesting the aspects of the PointNet. Is this clear? So since we are running out of the time, so we're gonna continue discussing the idea of the PointNet. We're gonna wrap up this next Wednesday, and we're gonna also continue discussing the PointNet++ and other the variants of the PointNet. And we're gonna also move on to some kind of the ideas. So like not just like taking the point cloud as the input, but also generating the point cloud as the output as well. Any questions on this? And if you have some more questions on the lectures or the assignments and the course project, please feel free to join the office hour and ask some more questions there. And I will see you in the office hour and also on the Wednesday. Okay, thank you.